Okay, so today we're going to do the second derivative test, which it's testing the relative extrema using the second derivative. So here's the deal. Second derivative is y double prime. And when you're talking about extrema, that's what we talked about in section 1, section 2. What are we using to find relative extrema usually? To find maxes and mins. Max or the min. That usually comes from, think about that for a second, think about what you think. What do we use? The original function, y prime or y double prime, mostly, to find max and min? Well, the answer is we use y prime. The reason is because that's the max and the min, it's going to be the critical numbers, or where the derivative is 0. That's going to be where a max is occurring, or where a min is occurring, or where the derivative is undefined. There's a max or a min there. Basically, the derivative is not 0 with these last two, but the derivative is undefined. So that's where a max and a min is going to occur, right? So what we're looking to do is take the second derivative and figure out something about the max and the min. So we're going to be mixing the original function, the derivative, and the second derivative all together. We can't keep them separate, so that's the biggest issue with this problem. This is just a quick note. A stationary point is a point where the derivative is equal to 0. It's basically just saying that the function is not increasing or decreasing. So basically what I'm saying is that, just remember this, if this is a y prime graph and this is plus and this is a plus and this is a 3 and this is a 0 here, it's not increasing all the way through, it's just increasing from negative infinity to 3. It stops increasing and then it starts increasing again right after 3 until infinity. So 3 is a stationary point. X equals 3. So let's get into this second derivative test. So let's find the local max and min using the second derivative test. Well, clearly, if it's the second derivative test, we need to find the first derivative, and then we'll need to find the second derivative. So I'm just going to kind of go. I think you're pretty good at this, and finding the second derivative, okay? Negative 60x to the third plus 30x. Okay, now the question becomes this. When is a possible potential max or min value? When does that happen? That's going to happen at a critical number. That's going to happen when, well, let's talk about that. It's really important that we understand when that happens. It happens at a critical number, and that is when y prime is equal to 0. By the way, this is not the second derivative, even though this is the second derivative test. So we have to take this, actually, and set this equal to 0 to find what could be a max or a min. So if we were to solve that equation for a few minutes, let's see, we could take out I guess we could take out a 15x squared, or even a negative 15x squared, and we'd have x squared minus 1, I believe, equal to 0. And our critical numbers would actually be x equals 0, x equals 1, and x equals negative 1. Those would be our critical numbers, our possible maxes or mins. That's where our derivative is 0. It's a flat point in the regular graph, but we don't know if they're maxes or mins. And typically what we do here is we make a number line, we find out the increasing and the decreasing, and figure out whether it was, plus to minus. If it was increasing, positive derivative, then negative derivative, it's a local max. If it was decreasing, then increasing, that's a local min, right? So that all makes sense. But instead, we're going to use the second derivative to figure this out. So what I want to do is I want to take these critical numbers, and maybe you should keep this as a note. So plug the critical numbers. This is an important thing to remember. The critical numbers, which is the zeros, undefined, from y prime into y double prime. That's what you want to do, okay? If nothing else, just remember that. So let's take those critical numbers and plug them in here. So basically what we're doing is we're taking these numbers, right? These numbers over here, and we're going to plug those into the yellow highlighted second derivative. So if I put 0 into that, what is the second derivative when x is equal to 0? well, we might need a little more real estate here. So the second derivative when x is equal to 0. So that's going to be f double prime when x is equal to 0. That's going to equal 0. You can see it. I'll mark this up a little bit. You put a 0 in here and here, you're going to get 0, right? So there's our first one. What about f double prime when x is equal to, and notice I'm taking these numbers right here, right? When x is equal to 1. Well, I'm going to take that and I'm going to plug it in over here again. So let me just kind of show you. Right here, right here. And I plug in the 1, I have negative 60 plus 30, I have negative 30 for an answer. And then I need to take my second derivative and look at negative 1. That's this number right here, right? You see it? And that's this guy. And we're going to take that and plug it in here and here. Well, when I plug in negative 1 in the first term, I actually get a negative 60 times a negative 1, which is a positive 60. Minus 30. So that's still, again, 30. So our values are 30, negative 30, and 0. So I just want to talk about concavity for a second. So this is definitely concave. If the second derivative there is negative, is it concave up or concave down? It's concave down. And this is concave up. So when x equals 1, right? When x equals 1, it's concave down. Concave up when x is equal to negative 1. Now this is the graph of y. It's concave down when x is negative 1 and up when x is negative 1. Concave up then. And we don't know. It's concave, concavity is uncertain. We don't know what it is. So let's just think about this for a moment, okay? Let's just think about these values. So let's say we have a graph here, and we don't really know what the graph looks like, but we do know that when x is equal to 1, okay, when x is equal to 1, we'll just get some kind of y value here. I'm making this up. When x is equal to 1, the graph is concave down. So the question then becomes, if the graph is concave down, doesn't it have to look something like this? And what does that tell you about this point? It's a max. Max if y is concave down at that x value. And visually that makes a ton of sense. We just looked at it. So this is our 1. This is this guy right here. We just talked about this. Concave down when x is 1. So this has kind of been taken care of. Okay? Let's grab a new color we haven't used. Let's take, when x is equal to negative 1, it's concave up. So I'm going to go to negative 1. I'm going to make a random value. It doesn't really matter where it is. I'm going to put it right here, for example. And I know the graph is concave up, so must the graph be, is the graph then like this, or is the graph like this? I mean, if we wanted the two, so concave up would mean the graph is like this, right? And if the graph is concave up here, well then that means that this is going to be a local minimum, right? It has to be. So we have a min if y is concave down, concave up. Y is concave up at that x value. So we've really figured out that we have a max of, I believe it was 1 comma something, and we have a min of negative 1 comma something. But we don't know what's going on with the 0. We're going to deal with that in a little while. But for right now, I want to figure out, if this is the max and the min value, I want to figure out what my original function was. So let me just grab that. And I want to figure out what the y values are, right? So now we're actually using all three functions in this type of problem. And this is what, I think this is where people have the most trouble, right? So we have a max when x is equal to, we don't need any of this stuff over here anymore. All we need is to find out what the max is. So it's 1 comma something. So it's really just f of 1. What's the y value that goes with that, right? Okay, so it is 2. So the max is 1 comma 2. And the local minimum, this is the local minimum, of course, f of negative 1. Well, that's negative 3. That's negative 1. That's positive 5, and that's negative 1. So that's 3 minus 5. That's negative 2. So our local min is there. So we found our local max and our local min from our graph. That is really what it was asking you to do. You're in pretty good shape. You could have another local max or min. We still have this unknown quantity here, this one. So what you're going to do when this happens, okay, what you're going to do when this happens is you're going to say that the test fails. If it comes out as 0, not negative, not positive, if it comes out as 0, you're going to say that the second derivative test fails. Test fails. And what happens is, sadly, you have to go back and remember that this is a critical number and take your first derivative and figure it out the old school way, the way that we used to do it, right? So now we're going to use the old way of doing things, which was to take the first derivative and plug into that to get our answer. So let's see if we can do that. Sorry, I'm all over the place here. Okay, I think we got it now. So let's look at where is our first derivative. Well, I'll rewrite our first derivative. It's over here. But again, things are getting messy. So f prime of x is equal to negative 15x to the fourth plus 15x squared. I want to test, I don't think I should test negative 1 or 1. Why do you think I shouldn't test those? Because they were over here. There were issues over here. And if our critical numbers actually are negative 1 and 1, we should really put them on our graph. Thank God I thought of that. So let's use like negative 1/2 and positive 1/2, something like that. Okay, so we put in 1/2 here. Let's say we put in positive 1/2. Well, we're going to have negative 15. 1/2 to the fourth is 1 over 16. And then we're going to have to add the 15, and that's going to be 1 over 4. The question becomes, is this going to come out positive or negative? It's going to come out positive. The derivative's going to come out positive, so we have an increasing interval there. Now I'm going to go ahead and do this one, okay, and I will take that into the one. Well, now I guess I have to the fourth power. Nothing is going to change, because this is still going to be positive, and this is still going to be positive because we have even powers. So we have a negative number, same exact number, to even powers. Everything is actually going to come out the same, and we know that this is going to come out positive. And I guess that makes sense, because the graph is going up, it flattens, and then it goes up again. So it's really not a local max there, which makes sense. It's positive slope, positive slope. Not always is that going to be the case, but in this example, that's how it worked out. Okay, let's see how we're doing here. So you are to try this problem, and here is the assignment. So just be aware, just pause the video if you're here right now. This is what you are to try. And then remember, if there's additional work in class to get that done as well. So give this a shot, and we will see you tomorrow.